Thank you. The backstory is there was a fresh new assistant professor at Penn State who was teaching his first geomorphology course. That's when I first met Dr. Potter because I was a student in that course. We have a lot of funding agencies that fund a lot of our studies, and I'm just going to move right into this. Green infrastructure, low impact development has been mentioned a lot today, and a lot of what we focus on at our field site, which is a very unique site. We can study stormwater infrastructure in parallel, plus we go to satellite sites and we do a lot of installations, and we have mountains of data, probably over 100 million data points to date. And if you think about it, with wastewater or drinking water or industrial wastewater, we use a lot of energy, a lot of piping systems, and we use very specific unit operation processes to improve the water. With stormwater, you're using gravity and a prayer, and you're hoping that everything turns out great. And you're expecting all of these types of unit processes to improve the water as it moves through the system. A lot of the more modern systems, the low impact development green infrastructure systems, may or may not have plants. And I'll talk about a bunch of these when I show a lot of the data. The permeable pavements, filtration systems, eco roofs. I know you have heard them called green roofs, blue roofs, eco roofs. The real difference between them all is whether or not you want plants and what you're expecting from those plants to do. Some of the other filtration systems will be using plants, and I know the focus in this particular symposium is trees, but in general, we kind of lump them all together, and after all, I am an engineer, not a biologist. In most of these systems, typically what you will see characteristically when I show you some of the field installations, there's pre-treatment, where you get out the shopping carts and the bicycles and all the big stuff, and then it goes to some type of a system where the water is going to be processed through and improved. At the bottom of those systems, you can either have infiltration or it can be plumbed into urban infrastructure, which is very, very common. So for example, it goes right into a catch basin or right into the storm sewer and then on its merry way. So this would be a new installation where you have a parking lot and what used to be maybe a grass strip in between. Now that's serving double duty as a bioretention system, and everything that was in the previous cartoon is existing in this slide. As far as a retrofit, and this is our biggest issue in urban infrastructure now. How do we sneak these into existing systems? What you're looking at is basically a little island. So one parking spot was taken away close to the intersection. And at that location, a bioretention system was installed. This is looking at it going uphill. Underground, it's plumbed into this catch basin, and then the overflow above ground also is plumbed into this catch basin. So you can see that there are plantings in this. They could be almost anything, but this is where we can sneak these systems in. This is also a retrofitted situation where you would have an island normally that had some trees in it. Now you've just taken away a small piece of the island and just put in a bioretention system. So these are pretty easy to sneak in. You've probably heard of street trees, tree box filters. All they are a specialized bioretention system. Functionally, they're basically the same. And as you can see, water would come in the surface. You have some availability for water to be stored above the surface. It flows through a filter media. It can go to infiltration, or it's plumbed into infrastructure. This would be the one that we planted at the Stormwater Center in 2003. That tree we used to call a sickly ash. It looks gorgeous now. It's actually a very healthy tree. In Boston, you can see how retrofitting these into the infrastructure is pretty simple to do. This is also a retrofit where the tree filter removed a catch basin. So what you see in the street along the curb line used to be a catch basin. Now the water goes to the tree filter first, and then it's plumbed back into the storm sewer. Vegetation, normally you look to the experts, the local experts. Maybe this is some place where you could actually start to look at more research at what might be the better species to do these things. We've seen everything from forest to meadow to transitional to ornamental. Ornamentals typically don't do that well, as you can expect, but that doesn't stop people from trying to use them. And then the other system, which is a generic system that I'll mention throughout the data slides, is called a subsurface gravel wetland. And probably the most unique features of this one One is that compared to all the other systems where water's moving vertically, in this case it's moving horizontally through stone. Secondly, because it's below ground, it's the only system that's running anaerobically. And that's really key, as you'll see later, for denitrification and removing nitrogen. And you start to see this concept now of an internal water storage or an anaerobic zone being built into the more modern designs for bioretention systems, trying to mimic the same type of a process. So as you can see, you will have nitrogen species coming in, and you actually need an aerobic zone because you want to convert everything to nitrate preferably. And then once it goes down below the ground, that's when you can denitrify. So those are key facets of this type of a system. And so this is what one would look like. It is a space hog, so you just can't put it anywhere in the urban landscape. If there are abandoned lands or some large places where you can put these, it's going to require a lot of landscape, but at the same time you can have maybe a little more diversity there. As I had mentioned before, this is a plot of on the left-hand side, dissolved oxygen. On the right-hand side, the vertical axis is the discharge. And this is just one storm, so time is on the horizontal axis. The blue line is the hydrograph, how the water comes in. And where we have our probe is actually a little further downstream from the system. And so in between storms, it's just sitting in a stagnant pool of water that gets aerobic. But once flow starts to come through, you can see how the DO just plummets. So again, it's an anaerobic system. The other thing we have to focus on in these urban systems is that if you want to name a contaminant, it's probably there. If you want to name a pollutant, it's going to wash off the surface, and they all wash off differently. Probably importance on this slide, nitrogen, like maybe oil and grease, runs off incredibly quickly. And so when you're designing systems, if the focus is on, for example, nitrogen, you're looking at maybe the first third to half an inch. That's where you're going to get most of your nitrogen. If you're looking at something like zinc or sediment or something else, you may actually have to be looking at bigger volumes. So now you really want to target the receiving water body. And when you look at the receiving water body, ask the question, what are my impairments there? And then design green infrastructure to kind of help that along the way. So for hydraulic performance, people have already mentioned this. A lot of the green infrastructure will take an inflow hydrograph and reduce the peak. And then the other thing it does will lag the peak. And so a lot of these types of hydraulic consequences really benefit the combined sewer overflow and flooding problems that people were talking about earlier. You can look at ratios of the flows, ratios of the timing of the center of mass as factors, and you can kind of stack up infrastructure. And so if you want a certain hydraulic performance, you know exactly the kind of green infrastructure you need to install in order to get the hydraulic performance you're after. So for example, the tree filter. This is one of the ones we've been looking at for about 8 years now. And you know what you can see here is the 100-year storm. So during our time we had something very, very close to the 100-year storm rainfall event, the Patriots Day event as it was known up in our neck of the woods. And you had a volume reduction of about 13% and a peak flow reduction of about 16%. So on the really large events, you're not going to get an enormous amount of peak flow reduction because you don't have a lot of storage. For the much smaller events, you can see that you can get fairly significant peak flow reductions. So something around these events, these are less than the 2-year events. And so for the smaller events, you may see a lot of volume reduction. On this particular event of 1.2 inches, we saw no volume reduction. Why? Because it rained the last 3 days, the previous 3 days. So obviously, if everything's saturated, you're not going to get the kind of volume reduction you're after. Is there a soil limitation? We've looked at the consequences of climate change, and we've compared side by side conventional build out with storm sewers, curb gutter, catch basins, and we've compared that to GI designs. And without going through all of the specific details, what you would see is on a very busy slide, the green bars are going to be pre-development. The gray bars are going to be post-development, and the light blue bars, and the gray bars are the conventional stormwater runoff. So again, green is low impact development, light blue is pre-development, what you'd expect from a natural system, and gray is conventional. And we're comparing two simple things, the volume The first few sets of bars are existing hydrology. The next, where you see ADJ adjusted, are what we're expecting with climate change. In our neck of the woods, it's wetter. And what you can see from these is that whether you're looking at a very permeable soil or a low permeability soil, with green infrastructure, you can actually get more infiltration into the ground than pre-development conditions. So the technology is not a constraint. It's the backbone and the political will to actually move forward with these types of technologies. As far as performance, busy slide, and I'll show a few like these. These are the average performances of pollutant removal. And so what you're looking at, in this case, total suspended sediment removal. The blue bars are what you would consider conventional infrastructure, swales of different types and ponds. The light blue bars are manufactured technologies which kind of fit into the guise of green infrastructure. They're manufactured typically because you can't put them above ground or you're space constrained. And then the green bars are the typical green infrastructure you would see: bioretention, tree filter, the gravel wetland, and permeable pavements. And so for total suspended solids removal, you see a great performance by the green infrastructure, and a typical standard is 80% TSS, time-honored standard. For total phosphorus, a similar type of a diagram. What you see is some of the manufactured designs can do fairly well at removal of phosphorus, and the green infrastructure can also do fairly well. The conventional technologies aren't doing so well at phosphorus removal. And then when we go to nitrogen, typically what you're finding, as you would expect, is that the systems with plants will outperform those that don't have plants. So for example, a porous asphalt, while doing great at total suspended solids and phosphorus, actually you get export of nitrogen from those types of systems. You get more nitrogen out than goes in by stormwater because of atmospheric deposition. These are probability distributions. The last three slides were just the mean, the median. These slides show that over the entire probability distribution, we can look at these same systems, and the systems are classified. First, you have the black line, that's the influent, and our site is basically a parking lot. It's 95% impervious cover, 9 acres of asphalt. And the probability distribution of all the total suspended that comes with it would be a distribution that sits to the right of everybody else, meaning that if all the other distributions are to the left, you're removing sediment in this case. And so you have filtration systems with plants, and then just sedimentation, which is the typical conventional. And so you can see conventional will remove some sediments. Enhanced sedimentation, which are where some of those hydrodynamic separators actually don't do that well because they only really remove the large sediment, and most stormwater runoff is fine sediment. And then the systems that do filtration with plants actually do a great job at the sediment. For nitrogen removal, a mixed story, and again, it's a story that I had mentioned before. The black distribution is the influent. That's what's coming off the lot. Some systems you see more nitrogen coming out. And again, that's because they don't have plants, they don't have a method of removing the nitrogen. Whereas the system with plants are actually doing a better job at removing nitrogen. And basically the same thing, same kind of a story for phosphorus. Not all systems are going to give you the same performance, but we certainly have that data. All right, this is an incredibly busy slide, but it's looking at some of the deeper issues you can start to tease out of real-time data. Ultimately, the water is going to go to a receiving stream. And so what we have here is a corellogram, if you're familiar with corellograms, and it's basically identifying the memory. And the memory we're looking at in this case is temperature. But you could be looking at dissolved oxygen, total dissolved solids. Any time series is going to have a corellogram. And so we have 5-minute data, and the dashed lines are first order stream in our neck of the woods. And so you can see the temperature memory, and this is summer temperature, so we distinguish summer from winter. The temperature characteristics, and the diurnality is clearly evident in the data. And then you can see, for example, what a retention pond memory is for temperature, grass swale, porous asphalt, and the subsurface gravel wetland. And what you're seeing is some systems do a very good job of matching the memory characteristics of natural systems. And other systems, and of course these were conventional technologies, were about the worst thing you can do. And basically they're representing how flashy these systems can be. One of the barriers, and one of my last slides is on barriers, is a lot of people challenge or don't understand how these systems work. And in the cold part of the country, they will start to look at, well, these systems must freeze, so they can't work all the time. We actually use frost gauges like the one we're showing here to actually measure frost penetration, not only in the native soils, but in all of our systems. And another very busy slide, but what you have is frost penetration depth on the left-hand axis, the average daily temperature on the right, and then we have a bunch of different systems. And anytime it rains, this is 2005, January to March, even in January, we'll get a rainstorm. We're close enough to the coast. And what you see is some of these systems will freeze, so you get a frost penetration, but at the first amount of runoff, they thaw out almost instantaneously. So that's fine. In fact, some of them are just frozen porous media. For example, the permeable surfaces are frozen, but they still have porosity. Others, like the bioretention, will be frozen at the surface, and it's almost an impermeable block. But once you get the runoff sitting on top of it, it thaws out very quickly. So the performance in the winter is great. This would be an urban system in Rochester, New Hampshire, where we actually put in a lot of LID. And in this case, we put in a porous asphalt basketball court, the bioretention, tree filter, and infiltration, and a pervious concrete sidewalk. Many people have mentioned, how do you measure the ecosystem services or the social capital services? The happiest people with this were the teachers. Why? Because in the spring, this is the playground and it was a swamp. Now the kids can actually go out for recess, so the teachers don't have to sit with them during the classroom all day. There are a lot of benefits, and again, it's easy to sneak these things into the urban infrastructure. Again, it gets back to the backbone and the political will. We can certainly target, and we've done this on a watershed now. We've taken a watershed from 32% impervious cover down to about 9% effective impervious cover by putting a lot of the runoff through stormwater infrastructure. So you can actually identify where you have impervious surfaces, and this is the Rochester watershed area. With that, you can identify loading from the different types of impervious cover to look at basically where the largest loads come from, where you should really be investing your fortune for infrastructure so you get the biggest bang for your buck. And then trying to get after the low-hanging fruit. Costs, we can identify costs. And you can certainly see when you look at costs, in this case, a table in dollars per area of imperviousness, conventional technology is typically the cheapest. But that's maybe not the best cost measure. We've also done a thorough study of maintenance. And typically for LID, green infrastructure, it's some of the cheapest maintenance. But the real value, if you want to compare a metric, is the cost in dollars per pound removed of your pollutant per acre of your watershed. And when you start to match this up, here you see the left-hand scale is that cost from $25 to $34 for different technologies. But when you go to something like nitrogen, you need to start using a logarithmic scale, because if you don't get out nitrogen, the cost per pound just skyrockets. Okay, and so again, when you're starting to weigh these costs, you really need to think about what's your objective and then matching technologies to that objective. Don't throw out green infrastructure for the sake of green infrastructure. There's a lot of hidden, unconsidered costs that typically don't factor into a lot of our economic decisions. Usually it's capital cost, and that's what we make a lot of our decisions upon. And when we do that, what it really means is if you go in and allow land use development to occur, the rest of us are going to subsidize that. That's what's going to happen, because ultimately, if you don't think of the water quality or what's happening in the urban systems, ultimately, we're going to be challenged with fixing it. And usually, that's not whoever did the development. There are a lot of ecosystem services people have mentioned here already today. One of them I'd throw out there is pet waste management. If you think about it, with all the pets in urban systems, this is not a trivial issue. We can have a scooper law, but you can't have something to clean up liquid waste. So these greener systems actually do a better better at the nutrient or nitrogen management. Human dimensions, people have talked about these also, so I won't add to them. Barriers, and this is, I think, my last slide. For the barriers for green infrastructure, and we have 3 projects now in trying to understand why it's not being implemented. The science is there, but it's not being implemented. And the reason is it's because it's not part of our DNA when we make land use decisions. And that's what we have to do. How we get it to be part of our DNA is a challenge. For example, the impossible challenge, what is that? Well, I'll give you a classic one. If you're going to design a permeable surface like a porous asphalt parking lot, a planning board may say, well, what if you spill 1,000 gallons of gasoline on it? Well, the answer is you're screwed. But what happens when you spill 1,000 gallons of gasoline in a curb, gutter, catch basin, sewer system? It goes right to the stream directly. In that pervious system, you actually have containment. Okay, and so that impossible challenge is thrown at the new technology. It's never thrown at the existing technology. And then a lot of these other barriers are ones that we typically run up against. Turf management, what I mean by that is, and this is an example from where I have a house in State College. It's in the historic district, 200-year-old maple tree in front of the house, and half of it fell on the house last year. So last summer they took it because they felt it was a high-risk tree, and they're going to replace it, and it's the perfect place for a tree filter because there's a catch basin right there. But the tree committee and the stormwater committee might as well be in different planets because they're not going to do the same thing. And so a tree will go there, but it will have nothing to do with stormwater management. So I think I used all of my time.